these bit-defined systems. Thank you, Tarek.
Hope you had a nice lunch. Okay, so where were we? Maybe it feels like forever ago, but let's just recap a little bit before we get started. So, we were interested in understanding this phase of matter, which I guess every single one of you has dealt with, which is glass. And we decided to model it by imagining we have a bunch of spins on a lattice, but the idea of this lattice is not super important. And we considered Hamiltonian, where we coupled the spins in a particular way. And this J was a bunch of positive and negative numbers. And the fact that this J was taken from some random distribution meant that the actual state of the system was some very complicated configuration, and it was impossible to satisfy all the bonds, because you go around the lattice, you might satisfy some of the bonds, but most of the bonds may or may not be satisfied. And the fact that it's basically impossible to satisfy all the bonds of this system made the configuration space very rich. And we saw, by analyzing this model, so let me also remind you that we had some probability distribution over the couplings, because we couldn't solve this model in general, so we had to solve this model on average. So we took these couplings to be sampled from some distribution. We solved the model on average. And what we uncovered over the course of a few lectures is that we had to consider a very strange order parameter, which is the overlap between configurations in a replicated set of systems, and that these overlaps could develop a very non-trivial structure. And this very non-trivial structure was the indicator that we had gotten into a new phase. So what we found was, for this model in particular, the overlap matrix took this particular form. And this is a size M by M matrix, M, and 0. So the state space organized itself in a particular way. Actually, what's interesting about this system is that it tells you that all distances are either u or 0 between the states. Most of the distances are 0, but sometimes some small subset of the states can be in a local basin. So what you should really imagine is that we have a free energy, and our free energy looks something like this. So I don't understand what I'm supposed to do. Why does that make a difference? Ah. It's not in this. What is the point of this thing? It's branding. Yeah, baby. I'm repping video. Buy video. Don't be a Dio. I don't know what that means. Yeah, so you should really think that maybe the state space, the free energy state space, looks something like this, and there are some basins where the states are kind of close to each other, and then these states will always be far from this state. Of course, the picture is much more complicated than that. This is a very very simplifying way of drawing the free energy landscape. The free energy landscape is multidimensional. It has a lot of flat directions. But as far as these overlaps are concerned, it's telling us that there's a hierarchy. There are some states that are close, and otherwise all states are far from each other. Okay. And one last thing I want to remind you of is that this overlap is an angle. Remember, it's the dot product of two vectors normalized to be root n divided by n. So it's a cosine, so it has to be between -1 and 1. And this m we found had to be between 0 and 1. And these were our order parameters. And just by way of nomenclature, so that you know, this U is called the Edwards-Anderson order parameter, based off the authors that proposed it. Okay, so now we solved this model. We found this order parameter that told us that we were in some new thermodynamic state, which we would like to call the spin glass state. It has an associated temperature where these overlaps kick in. But if you remember, in the first lecture, I emphasized that we really like order parameters that experimentalists can actually observe, and where there's a sharp signal. Measuring this U is, well, you have to imagine what you would have to do to measure it, right? You have to take your system, you imagine fixing the couplings very precisely, then copying the system with the exact same couplings, let the system equilibrate thermodynamically, compare the two, and then do that over a whole sampling of these couplings, and then look at the average overlap. And you have to do this a bunch of times and see whether or not you get U or 0, and the proportion of the amount that you get that's U will be M, and the proportion of the amount that you get 0 will be 1 minus M. So that's a very difficult experiment to do. If you go to your experimental colleague and tell them, all right, let's do this experiment, they'll laugh at you. There's no way that they would ever consider doing it. So, so we have to be more clever. And I'm going to spoil the final message, but we're not going to do very much better by the end of the lecture, but we're going to get a little bit epsilonically close to something that is more accessible to an experiment. Okay? So that's where dynamics comes in. That's why we're going to solve the dynamics of this model. Okay, so what do I mean by dynamics? So I have to remind you about some stuff. So, yeah, so let's start from the basics. So, all right, I know you guys just had lunch. It's been a long 2 weeks. But what tells you that this is not a dynamical system? Very good. There's no time dependence. So we need to add time dependence. But we also want this system we also want this system to be at finite temperature. So we're going to do the following. And I'm going to explain slowly so that it's clear what I'm doing. So we're going to consider sorry, the following action now. And this is a Euclidean action. So what that means is that this tau is not real time, what we would observe as the time that elapses, for example, in this room. What this tau is sometimes called imaginary time. Condensed matter theorists love to call this imaginary time. And there's a nice fact that I'm going to review that computing this path integral, where I'm going to take the boundary conditions, sigma I of tau, identified with sigma I of tau plus beta, is still computing for me the thermodynamic partition function, but for the time-dependent system, where the spins are allowed to fluctuate in time. Okay? Does anybody remember this fact? Is this, does this look surprising to you guys? Have you guys seen this? You haven't seen this? How many have seen it? Okay, a few of you. Some of you are not raising your hands, so I'm gonna review it anyway. Okay, the argument is kind of simple. So I'm not gonna. It'll take me just a few lines. So you have to remember that in regular quantum mechanics, we're interested in computing transition amplitudes from a state phi1 to a state phi2 in a time t. So we insert this operator e to the minus I h t. And this transition amplitude is computed by a Lorentzian path integral, e to the I s Lorentzian of phi, with the conditions that phi at 0 is equal to phi 1, and phi at t is equal to phi 2. Right? You guys remember that. That's a basic definition. Okay. And now, what I'm going to do is I'm going to take t goes to minus I tau, and so I have that phi 1 e to the minus h tau phi 2 is now given by the Euclidean path integral. Okay. Now the last thing I'm going to do is that I'm going to remind you that if I want to compute trace of e to the minus beta h, then all I need to do is set phi 1 equal to phi 2, and then integrate over all the possible phi 1s and phi 2s. That's how I'm computing the trace. So that's the sum over phi of phi e to the minus beta h phi. And I got that by doing the Euclidean path integral, where now all I have to do is integrate over all configurations where phi of 0 is equal to phi of beta. Okay? So we're going to do the same thing here. We're going to do the path integral over all configurations where sigma is identified. Sigma of tau is equal to sigma of tau plus beta. And that's going to compute for me the thermal trace of this field, but now it's going to incorporate dynamics for sigma. Of course, this time dependence is imaginary time. It's not real time, so it's not the time dependence that we'll uncover in an experiment. But I'm going to explain to you, either this lecture or the next, depending on how far we get in the hour and a half, how we can analytically continue the results from this theory to get the real-time dynamics. Okay? So that's the goal. So we're going to study this model with imaginary time dynamics, and then we're going to slowly develop how we turn those answers into ones that give us correlation functions in real time. Because, of course, if you told your experimental friends, go and do an imaginary time experiment, they'll laugh at you also. Okay, is that clear? Okay. Are there any questions? Okay. So, I know the last few lectures there were a lot of I went into all the gory details. We solved this model without the time dependence. We're not going to do all of that again because it would take forever. We don't have an infinite amount of time. But hopefully, it should be clear that, or at least the steps should be familiar enough to you that, that what I'm going to say right now is not too surprising. And of course, if you want me to fill in any steps, just let me know. Okay, so what we did before was, remember, we wanted to compute the thermodynamic free energy, which is the log of the Euclidean path integral, and then do the average over the disorder, and then we'd have the free energy. But we didn't know how to do the path integral for general couplings, take its log, and then do the integral of the couplings. So we introduced these replicas, and then we integrated over the couplings, and then at the end of the calculation, we took the replica number to 0. Remember that? Thank you. Okay, so we're going to do the same thing here. We're going to have to introduce replicas. We're going to introduce an integer number of replicas, and then we're going to write down an effective theory of the meson, or this replica matrix. And the steps follow almost exactly as before, except now we just have to deal with the fact that there's a kinetic term, and this matrix is going to be time dependent. So the first difference is that the effective theory will be of a QAB of tau prime, which is exactly the same as before, only with time dependence. And these two guys can be at different times. So the matrix will depend on 2 times, not just 1. But one nice thing is that, oh, and there's a disorder average here. One nice thing is that if I consider Q of A not equal to B, well, remember, these are 2 different replicas, so the thermodynamic average splits. And because these are one-point functions in their own replica, there's no time dependence, right? One-point functions, by time translation invariance, don't have time dependence. So all the time dependence in the off-diagonal part goes away. So the off-diagonal parts of this matrix will be just as before. There's no difference. The only place where we're going to have time dependence is in the diagonal part. So this matrix now is going to look something like this. There'll be an M by M. There will be Q's along the diagonal. I'll repeat. And there'll be 0. So the diagonal part will just be one function called Q of tau prime. The off-diagonal parts will be as before. I'll call it U. And then the guy over here will be 0. And this Q of tau prime, as I was saying, by translation invariance, will just be a function of tau minus tau prime. Okay. Now, I want to gauge your intuition a little bit. So remember, there was also this spherical constraint that I had to consider. So these sigmas are dimensionless. So we had to introduce a dimensional parameter over here. We could canonically normalize this, but this spherical constraint, when I presented it before, made the field dimensionless. So now the kinetic term has a dimensional constant out front. And I want to ask you, in what limit will I recover the time-independent physics? Remember, before we could ignore the kinetic term, or before we were ignoring the kinetic term. So what limit of this theory do I expect to recover the static physics? Beta to infinity. I want it in terms of this quantity m. Who agrees with that? Who thinks m to 0? All right, who thinks something else? It's Brazil. Voting is mandatory, as we found out. So please vote. Who thinks something else? Who doesn't know? So m to 0 so that we can turn this off. That's what you guys think. It turns out that the correct answer is m to infinity. Gives the static answer. Why is that? Let's think about it. Remember, you're weighting paths by e to the minus Euclidean action, right? E to the minus s. And sending m very big puts a big cost to making this field move, to giving it wiggles. So if m is very big, the field wants to be very static. So m to infinity is the limit that gives you static physics, not m to 0. It's counterintuitive. That's why I asked the question. Turning m to 0, it looks like there's no time derivative, but that's actually the wrong answer. Okay. So, I'm sure you're all experts. So, what exercise was I on? Exercise 8? Exercise 8. I heard there's an exercise session today, so I'm sure you're going to get to this one before the end of it. So, show that the effective action of Q is And this trace is not only over the replica indices of the matrix, but it's also over the tau and tau prime indices. Now, it's now a matrix in continuous time variables and in replica space. Okay, so this is basically what we had before. The time dependence was gone. There would be no time derivative. We had this QAB to the P. we have this trace log of QAB. And this is just, I've added these Lagrange multipliers to enforce the spherical constraint. Spherical constraint tells you that at 0 time, remember this is a time translation invariant function, at time equals 0, the function should be 1, this 2-point function, by the spherical constraint, and it can decay from there. So the steps that lead to this, you basically follow exactly the derivation of the static case. The only extra step you need to keep in mind is that now there's time dependence. Okay? So this is okay, right? This is familiar enough, looks close enough to what you saw before. No surprises. So now the only extra thing we have to deal with is the fact that the diagonal part has a kinetic term. And we're going to study the equations of motion of this theory. Actually, the equations of motion of this theory are very complicated. Even when you pick the right ansatz, they're very complicated. So now I'll give you exercise 9. And this is difficult. So the exercises derive the equations of motion. So one thing you learn when you study a theory like this in Euclidean time or imaginary time, as condensed matter theorists like to call it, is because these functions are periodic in the Euclidean time, their Fourier transforms are Fourier transforms over a discrete set of frequencies. You guys have seen that before? Anytime you have a periodic function, the Fourier modes are discrete. So this function Q, you can write in Fourier space 1 over beta. So this normalization is a convention. So these are the Fourier modes. And these guys are called the Matsubara frequencies, omega k. What is that? Sometimes called minus I omega k. Pull the I out. They're a discrete set. And we're going to write down the equations of motion for the Fourier modes rather than the time-dependent part. Contains the same amount of information. And in order to do that, I'm going to need to define a couple of functions. So one is, I'm going to define a function called lambda, which is just q to some power. And it also has a Fourier transform. So because it's q to some power, lambda hat will be p over beta Kp minus 2, sum over a bunch of these k's, q k1, q k2, and then, of course, there is a momentum conserving delta function, which we can integrate over k1, k minus k1 minus kp minus 2. And finally, I'm just going to introduce one more function. I'm going to call it QR. And QR is just Q of tau prime minus U. And lambda R is also lambda tau prime minus p over 2 u to the p minus 1. So above the spin glass transition, QR and Q are the same. But below the spin glass transition, when you get a U dependence, all of a sudden they just differ by a constant for both of these. And once you have defined these, then the equations of motion are as follows. And the same equations, so the equations for U and M are the ones that I derived in the previous lecture, except now we replace ones everywhere by Q hat 0 over beta. So I'm not going to write all of them, but for example, delta of U, the equation of motion that you get from varying U, is m minus 1 over 2. So if you go back to your notes, you'll see that the only thing I've changed in this equation is that there used to be a 1 here, and now there's a q hat of 0 over beta. And incidentally, q hat of 0 over beta is just the integral from 0 to beta, 1 over beta, of q of tau. It's the 0 mode. So q of tau used to be 1. The integral over 1 from 0 to beta is beta, so beta over beta is 1. And now we have a non-trivial time dependence, so you just need the integral of q over here, over time. And now we need to solve these equations. And this is a very complicated coupled equation for the q of k. Remember, these lambdas are some huge products of q's. There's no way to solve this by hand. It's a very complicated equation for the modes of this function. So the best thing that you can do is put it in a computer and try and solve for the time dependence of this q. And so, like I said, there's no functional form that I could derive for you, but I can show you some plots. Where's my eraser. So need to solve that numerically. Very difficult problem. Okay. So let's see if you're paying attention. Where must this Q of tau start? If I'm plotting Q of tau, sorry, this is tau over beta. So where must Q of tau start? T equals 0. Starts at 1, that's the spherical constraint. And then what do you expect it to do? So 2-point function, what is it measuring? It's measuring the average of, remember this, sigma I in one replica, say 1 of tau, sigma I in replica 1 of tau prime, averaged for all of the system. So what is it measuring? It's measuring, say I hit some spin, and I ask what is the value of the spin later as I evolve in imaginary time. You should expect that things should be very correlated at early times, and then it decays. Right? So the behavior is that it just goes down. And actually, because this has to be a periodic function, it has to come back up to 1. So this is 1/2, and then it goes back up. And this is just the periodicity. So you expect it to decay, and just because this is a periodic function, it'll come back up. Okay. And if you solve this equation in the computer, you see exactly that, if you've done things correctly, at high temperatures. So T much bigger than T critical. This thing decays basically to almost 0. It can't decay all the way to 0 because it has to come back up, and then it comes back up. But then, if you crank the temperature down, you'll notice something. So this is some T above Tc. This is another T above Tc. They follow each other. And then I keep lowering the temperature, and they keep following each other. And then all of a sudden, I hit the critical temperature, and something happens. This thing decays until the quantity U, and then comes back up. It doesn't go to 0 anymore. And this is a surprise. This was a surprise to those who first studied the dynamics of the system, because remember I told you that this quantity U, in order to measure it, I needed to take my static system, replicate it, compare, let it thermally equilibrate in both replicas, compare them, do the average over the disorder, and then do this a whole bunch of times so that I get good statistics. And that was the only way to measure U. But now, what you seem to find is if you have access to imaginary time experiments, then if you can just compute a correlation function of the spins, then what you would find is that there is a sharp signal of the transition in the correlation function. It doesn't decay to 0, it decays to exactly the Edwards-Anderson parameter that we had found before. So there's an imprint. And this is actually something that, if you think a little bit about it, isn't too surprising. So what a two-point function tells you is that it tells you the response of a system to being perturbed, right? And if you perturb a system that has trouble equilibrating, then there's no guarantee that it's going to go back to the same state that it was in, right? And what this non-trivial correlation function is telling you is actually it's possible to perturb the system and then end up in not the original basin that you're in, but a close one. And this is what the fact that you end up with U at half the thermal period is telling you. That actually you only need access to one replica, but you have to be able to do this experiment. Is that clear? Okay. So, why don't we tell our experimental colleagues to do this experiment? Yeah, you still need to be able to analytically continue yourself. And that's kind of difficult. So, I'm going to spend a little bit of time telling you how we set up the problem in real time. So, it would be very convenient, actually, if if we had an analytic solution to these equations of motion, because then I could just analytically continue the solution itself and then easily measure compute the correlation function in real time. It's just I get it as an analytic continuation of the imaginary time guy. But I went through this whole process to tell you that, well, it's actually the solution to some crazy difference equation for the frequencies. And these frequencies are these Matsubara frequencies. And this is not the function that I would solve for to get the real-time correlator. And I remember I had to solve this thing numerically. So I had to tell you how to analytically continue the equation so that you can solve it numerically again, rather than telling you how to analytically continue a numerically obtained function, because that's impossible. So, yeah, over the next few minutes, I'm going to try to tell you the thinking that leads us to be able to analytically continue the equations rather than analytically continue the plots. Okay? Correct. Well, if you're powerful enough, you could try to solve this analytically in Euclidean time. And then once you have that, you could analytically continue it. But because we don't have that, we have to do a little bit of work. Well, no. Sorry, I'm going to take my sweater off because I'm kind of warm. No, it's not possible to analytically continue a plot. You know what I mean? Like, so, this is very standard stuff. And it's well understood what is needed to analytically continue these functions to real time. And I'm going to explain. There's a beautiful theory of it. It's a standard thing to learn in quantum statistical mechanics, because people care a lot about doing real time thermal systems. So. But indeed, I mean, once you're stuck computing things numerically, then there's no analytic continuation that you can do of the numerically obtained plot. You have to start over and solve numerically, but for the Lorentzian problem.
How quickly the plots approach this one as you lower the temperature? Is that fast or not?
Yeah, very good. Okay, so let me answer that question in 2 ways. So, so there's 2 parameters now in our model, not just one. And yeah, so we have the temperature and we have M to tune. And I just want to show you the phase of this model. So this is disordered. Out here, in here you have spin glass. So 1 over m is 0 is m to infinity. So that's like the static case that we saw before. So the first few lectures were on this line, and there's some critical temperature over here. But then the question is, how do you approach the spin glass phase? Do you approach it this way? Do you approach it this way? Do you approach it this way? And depending on how you approach it, you get different behaviors. But in general, the behavior near the spin glass transition is close to exponential. There are some situations where the decay is polynomial to this number, but it kind of depends on the approach to the transition line. Fast, yeah. I mean, it depends. Sometimes it's slow. Sometimes it's polynomial. Any other questions? Okay, so and I drew it this way because you can look. This solid line is where the transition is second order, and this dotted line is where the transition is first order. So second order means that the parameter m, remember this parameter m, varies smoothly along this line and then jumps along this line. Okay. So this is we have a reason to rejoice. What we thought was inaccessible, an inaccessible parameter experimentally may be accessible if we had access to imaginary time physics. Unfortunately, we're real-time people, so we have to see whether or not it's accessible to real-time physics. And so, but in order to get there, I have to give you a little bit of foundation in order to understand how we're going to analytically continue these equations. Okay? Is that okay? Is that clear where we're going to go? No questions before I go? I'm going to take a little detour to give you some background right now. I'm going to keep those equations up here. I'm going to delete this blackboard. But you see, like, it's kind of cute. We started having no hope because this experimentally, there's no way to do this experiment where you do this replication thing. And then we just shut up and calculate. We compute a 2-point function, and all of a sudden there's hope, right? So don't ever despair. When you feel like life sucks, shut up and calculate. That's the answer. Okay, so imaginary time we want to compute, so I'm going to compute some correlation function. I'm going to call it g of tau. And remember, the g of tau, being an imaginary time object, is the trace over the Hilbert space of e to the minus beta h times some operator that depends on tau and operator at 0. And this operator at tau we get by acting with the Euclidean time evolution operator. So this is e to the h tau of 0, e to the minus h tau. So this is not a unitary operation. We're not acting with unitaries. E to the IH is unitary, e to the h is not unitary. But this is what we do. This is what we mean by evolving in imaginary time. Okay? So now, what we do is we insert a complete set of states here. M. What did I do in my notes? I think I introduced N here. And we introduce a complete set of states M here. And the trace is over another complete set of states. So we can write this as the sum over n and m, e to the minus beta en, e to the en minus em tau, and then n O of 0 m squared. Is that clear? Do you want me to give more details on that? I just inserted this complete set of states, which diagonalizes the Hamiltonian. And remember, I used that I have E minus h here and E plus h here, so it's En minus Em of tau. And I have a minus beta En. And then I just need these overlaps. Okay? So that's my time-dependent guy written in the basis of the Hamiltonian. Okay? So this is just nothing new here, standard stuff. Now I'm going to write G hat at the Matsubara frequency omega k. And that's the integral from 0 to beta. Am I missing a 1 over beta? No. Of e to the plus I omega k tau, g of tau. So if I plug that integral into here, I can just do it, and I would get so all I did to get to this line was I plugged in g of tau in this basis, and then all I have to do is I have to do an integral from 0 to beta of this. And that's just the integral of an exponential. We know how to integrate an exponential. It's very easy. and we get something that looks like this. Okay? So, nothing surprising, and I haven't learned anything yet. I've just written something down. I'm manipulating symbols. But we're going to see that this type of manipulation is going to give us the ability to eventually analytically continue the quantities that we want. You just have to be patient. Okay. So what's next? So I want to massage this formula. And in order to massage it, I'm going to introduce a function. So this is very much like the manipulations Dio was doing during his lecture for the Chow and Lehman decomposition, but I'm gonna take it a lot slower, step by step. Okay, so now I introduce a density by hand. I'm going to define a density rho omega, and I'm going to call it rho OO because it's really the density for this operator O. I'm going to call it 2 pi times 1 minus e to the beta omega, e to the plus beta omega, times sum over n and m, e to the minus beta en, times the delta function omega minus en minus em, times n o m squared. Okay? So I've just introduced this rho OO. And then I can see, just if I squint my eyes, that this g hat of omega k is now equal to the integral from minus infinity to infinity of d omega prime over 2 pi rho OO of omega prime divided by minus I omega k minus omega prime. So you just see that if you plug this formula in right here, you get this one back, right? So now this density, this rho, is a very nice quantity. Analytic continuation of the theory usually involves computing this rho for your function. It'll involve this intermediate step of trying to define a set of equations for rho, and then rho is nice because it can be extended to the entire analytic plane. It won't just be evaluated on the Matsubara frequencies. That's what will allow us to analytically continue. Okay. I want to keep this on the board, so I'm not going to touch this. This is a horizon over here. Okay. So I'm going to do one more thing. So now I have g of omega in terms of the Matsubara frequencies in terms of rho of omega as an integral, as a continuous integral. And now I just, as my last step, I want to write down g of t, or of tau, in terms of this rho. Okay? So that's the next step. So now remember, g of tau is defined as 1 over beta sum over k e to the minus I omega k tau of g hat of omega k. Right? That's just the definition. I have a function in frequency space. I just sum, multiply by the Matsubara frequencies. And we're going to compute this. So if I just look at the omega k dependence of g of omega k, the thing that I need to compute, so I need to compute sum k from minus infinity to infinity of e to the minus I omega k tau divided by minus I omega k minus omega prime. Right? If I can compute this sum, then I have g of tau in terms of rho. Right? And I'm going to do that, and I'm going to put a 1 over beta here, just because. I'm going to do that using something called the Poisson resummation formula. You guys have seen that before? Poisson resummation formula? No? Well, while you're sitting here, if you want, you can pull up the Wikipedia page for it, because it's a very standard trick. So what you do is you rewrite this as the integral of a sum, and it helps you sometimes simplify your sums. Trying to remember. Yeah, hold on. Yeah. Yeah, sorry. Yeah, so the Poisson resummation formula lets you write, yeah, I don't really understand my notes right now, so. You have to trust that this formula is true. You can derive it from the Wikipedia page. So what happens when you write your notes at like 3 in the morning? Yeah, so the Poisson resummation formula is a formula that lets you write a sum by first doing an integral and doing the sum over the Fourier transform of the sum that you wanted to do. So I've introduced this integral over omega, and now, and this is the old quantity over here. It's the quantity on this side. And now I'm doing this as a continuous integral over omega, but now I can, and then I do the sum over n, and it gives the same answer. And now I'm going to evaluate this by contour, this integral. I'll evaluate it by contour. And you can see that if tau is between 0 and beta, I will only want to close this thing in the upper half plane, right? Because then I'll have a damped integral. I can close the contour in the upper half plane, right? So, so I want to close in the upper half plane, and I can only do that for the positive ends. Right? If I have negative ends, then I can't close in the upper half plane. Right? For negative ends, I need to close in the lower half plane. Right? And we're going to take omega prime to be positive now. So, so for the ends less than 0, the contribution is going to be 0 because there's no pull anymore. Okay? So if I close the contour in the upper half plane, then I get that this is equal to the sum from n equals 0 to infinity of e to the omega prime tau plus n beta, which is just equal to e to the minus omega tau over 1 minus e to the minus beta omega prime. Okay, so what this tells me is that g of tau can be written as the integral from minus infinity to infinity d omega over 2 pi of e to the minus omega tau divided by 1 minus e to the minus beta omega times rho o of omega. And this is nice because now I don't really have to worry about writing it as a sum over Matsubara frequencies. I can now write it as an integral over a continuous frequency. And this trick is the trick that lets us be able to analytically continue thermal correlation functions in terms of imaginary time into real correlation functions of real time. Okay? So we want to continue now to Lorentzian signature. And I'm already envisioning that I'm not going to be able to finish in the next 15 minutes, but that's okay. We still have one more lecture. So this is the general theory. So if I have a thermal correlation function, then all of the physics is carried in this structure function here, much like the Challen-Lehman representation of a correlation function for a relativistic quantum field theory. And this structure function, this density, contains a lot of interesting physical stuff. And not only that, because it's a continuous function of this quantity omega, I'm no longer tied to the fact that I have to think in discrete frequency space. And so developing these kinds of ideas is what lets us freely continue from Euclidean time to Lorentzian time. And it will allow us to now consider these equations in Lorentzian time. But before that, I still need to introduce a few more intermediate concepts. Okay. So we want to continue to Lorentzian signature, right? So So you see nicely that if I continue tau to IT, I can freely do that in this equation, right? I can now continue tau to IT, and there's still information about the temperature. Rho has some information about the temperature. It really depends on beta, as you can see. But also, here you have the Boltzmann distribution. So you haven't forgotten that you're in a thermal state. And you can now analytically continue tau kind of freely. But remember, when we continue to Lorentzian, there's a bunch of ways of doing that. There's not just one direction where you can analytically continue. So let me define a couple of functions. So we call G positive, G of tau equals IT plus epsilon, and we call G less, so this is of real time t, so epsilon here is always positive. And one last thing I want to remind you of is that when we do experiments, we don't just compute correlation functions. In the real world, we're only capable of computing commutators. Commutators tell us about the order of events. So we're not allowed to compute anything other than a commutator. So this is the same as saying that I'm only allowed to compute retarded correlation functions. And retarded correlation functions, so in a thermal state, the definition is trace e to the minus beta h of some time-ordered commutator of t of 0. Well, if I just turn the crank, I would find that this is equal to theta of t times the difference between these two functions. Okay? So now we have everything that we need. So if I look over here, everything will be written in terms of this density. And now I'm able to compute everything. So for example, if I want my frequency space retarded Green's function, I would be able to write as so this is what allows us to define the analytic continuation. Okay? So in the end, we're going to be interested in computing the retarded correlation function, which gets me to the next exercise. Next two exercises. What exercise am I on? 9? 10. Okay, exercise 10. So how do we analytically continue this equation? Well, we have 1 over QR retarded omega minus. So your exercise is to show that the analytic continuation of this equation is m omega squared minus j squared lambda r of omega minus lambda r of 0, where this quantity right here is sorry, and this should be an R. So you see, it's kind of annoying that, well, you'll show this in your exercise, that on the right-hand side, you don't only have retarded functions, you also have this positive part on the right-hand side. So this equation is harder to put on a computer than this one. Because you don't have that subtlety in imaginary time. So, yeah, I think I'll leave it at that. So before next time, I want you to think a little bit about how to derive this equation, why you have these bigger functions on the right-hand side. And I want you to also think exercise 11. Will we see U in QR R of t at late times? And we'll discuss that next time.
Okay, I'll start with the question. Can you you have okay? You have erased the information of Matsubar sum on the retarded correlator, and now there is an object which we are interested in, which is rho of omega prime. Can you remind me the relation between Q and rho of omega?
Yeah, Q is just a particular
Instance
G
of
G. So there will be a rho for Q.
Very good.
So I was a bit sloppy. I dropped the OO here. But so you can imagine replacing O with sigma, and Q is the rho sigma sigma.
Excellent. Other questions?
So in this particular model, you took you used this trick to analytically continue, but it was like hard to come with the answer. But in other kind of models, what do people usually do?
No, this is what people always do to analytically.
This is what they always do.
This is standard, yeah.
Okay, and if it's not possible to do that, then there's nothing you can do, basically.
I think it's usually possible to do it.
Okay.
If you have equations in Matsubara space, you can always do this analysis.
Oh, okay. Okay, thank you.
More questions? maybe I'm jumping to other thing, but this reminds me like a lot to quasi-normal modes in Lorentzians that the pulse gives the pad integral. So this is kind of the same trick, but applying in this context of crystal.
Yeah. Yeah, it's very
Okay,
similar.
Okay, so
Yeah, all we're doing is, we're trying to think hard at erasing the fact that we're summing over a discrete number of frequencies, so that we end up with something that we can continue. And these are standard tricks. There's no magic in what I'm doing.
I have one further question. Beta has not erased, right, yet?
Correct, yeah. So for example, here, it's here.
Ah, very good. Are we interested in the beta to infinity limit?
No.
Not particularly.
No. We want to keep beta because
Experimentalists
keep it.
know, yes. Okay, they put a heater, and we have non-trivial temperature. Great. Someone else?
I don't know if this is like very basic, but so to define temperature in quantum field theory, you have to calculate the correlation functions, but then you have to analytically continue to get like, is there always a relationship between analytic continuation and temperature?
Okay, so you would never have to analytically continue if you were infinitely powerful. So we want to compute something like trace e to the minus beta h, some time-ordered operator in Lorentzian, O of t, O of 0. And if we knew how h acted on all operators and we could just compute that, then we would never need to analytically continue. Now, that's the principle. In practice, we never are able to do that. We're never super powerful. So we develop tricks. It's sometimes easier to formulate the problem in Euclidean, and then we have to then figure out how to go back to Lorentzian, and so this is why we do all of this stuff. But in principle, you don't have to analytically continue ever. You just have to compute. This is just an operator, e to the minus beta h. It's a matrix on Hilbert space, and if you can compute it, then you're fine. Then you can work in Lorentzian time the entire time.
And do you know any kind of research which is done to become more powerful?
There's some old papers. There's books even on thermal field theory. Maybe you can look there. Kapusta. There are papers by Gordon Semenoff where they develop all of this theory. So yeah, I would say look there. I'm not an expert on all of these things, but I think that there are certainly more tricks than the ones that I've mentioned, because I'm only mentioning the ones I know.
Okay. Thank you.
I have one further question. I'm here. I changed places, so I'm different students.
Okay.
We will drop M, right? Perhaps or not. Is that something that I would think as physical?
M is physical. Yeah, M tells you how quantum the system is. So yeah, large M suppresses fluctuations.
Yes.
So there's interesting physics in M. But I can tell you that for M very small, there's no spin glass. So remember I showed you this phase diagram, T 1 over M. So you only get spin glass in here.
Yeah, you told us that large M was the regime we were
studying in the beginning.
yeah, okay. Okay, and in the experiment?
Well,
That's why I was thinking that you would take m to infinity in the end, just to get rid of it.
yeah, well, yeah, in the experiment, yeah, you can do that. You can take m very large.
Okay.
Nothing stops you.
Shall I continue, or do you have questions? Okay, we'll continue in private. Thank you, Tarek.
Okay, you have the exercises for 3 courses. We're here. This starts at 4:30.
Okay, it measures how quantum you are, but what is the experimental quant? Because temperature I understand, but this m.
Yeah, you should think of it like another coupling in the field.
Okay. A coupling that gets you into your Hamiltonian, something that allows more or less fluctuations.